So first question is, why this course, as you know, is going to be about tall buildings, right? This is right now, it's one of the hot topics, and that's why we want to say why tall buildings is a hot topic, right? Why do we need tall buildings? Many people are against them and have spoken a lot that the cities turn into concrete jungle. It's not good. You have too many buildings, traffic jam. All those kind of problems are definitely something that comes with the tall buildings. But at the same time, there is no other solution now for this world than to make tall buildings. And I just want to tell you why tall buildings are going to be so important in this part of the world in the next, let's say, 20, 30 years. First of all, obviously, we have this fascination of making big things, right from the beginning. We are only 2 meters tall, not even 2 meters. And we want to make things which are like hundreds of meters big. One would wonder why. It's just, a show of our greatness. People want to make huge things, even though we don't really need them, right, for living, especially in the old days. But people made big palaces, big doors, big roofs, big pyramids, just for showing off their strength and abilities. So that's one of the things. Right now also, the very tall buildings that you see are just a show of ability to make. Dubai, China, show of progress. They don't need them, surely. But they want to make them because it shows that they can do it. And then it's a competition to go higher and higher. So that's one of the things. This, for example, human being is only that much high. Why would we make a roof that high? No, nothing in between. Useless space. But they want to make very tall columns and put the roof over there, even though they only need that much space to work under that, right? It's just a way of showing your strength, your technology, your ability for greatness. So that's one of the background behind that. So a lot of things that you see are based on those tall buildings or the intention to make something really tall. So this is not tall enough, so they put a pedestal very tall, then make the building on top of that. No use, nothing in there. It's not even used. It's just solid place. It's not, nobody's living there, right? But they just want to make it tall. So at that time, tall was only possible by making it stone or solid, and then but not multi-story tall, as you can see here. Just tall, long columns, and then put something on top of that. And other stories, then there came other buildings, and even the statues had to be tall. Everything had to be tall. Halls have to be tall. The pyramids have to be tall. And of course, nothing in there. Inside you cannot even go. It's so narrow. You have to crawl. There's no space inside. But they make this huge place just for the effect. But now that time is no more there. Now we are in a different time where we need it. And the reason we need it is because of two things. One is population growth, and second is urbanization. Everybody wants to live in the city. Previously, people lived in the rural areas, single-story house, mud houses, whatever, caves, and all those things. Incas used to live. So if you go back to history, people used to live very simply in those. But now everybody wants to come and live together in a small space. So if you want to live all together in a small space, there is no space, so you have to go vertical. So that's the reason tall buildings are going to be very important. So percentage urbanization, that means now most of the world in the next 20-30 years is going to be urban. That means about 80% of the people or 80% of the population is going to live in the cities. So if they're going to live in the cities, 80% of the people, you are going to have to make many tall buildings for them to stay there and work there. So population growth also now is very high in many countries. So these countries, population growth and urbanization combined together create a huge demand for cities to make tall buildings, even just for simple living, not to show off, just to live. We need those. And you can see from here that the urban to rural population is now changing, and very soon it's going to be mostly is going to be urban. As you can see from here, most of the population growth is going to be urban. Rural is almost now saturated, it's not going to grow. So all of the future people are going to move or live in the urban, and you can see from here, huge, from here to here about 3-5 billion people are going to live in cities, right? Currently, only 1.5 or 2 billion. So 5 times more people, 4 times to 5 times more people are going to live in the cities. Obviously, single-story houses is not going to work. There's not enough land there. So tall buildings is the need of this century, especially. Previous century, it was some cities only, big cities like New York, Tokyo and all. This century, it's going to be the need of every city is going to need tall buildings. And you can see that gradually, all these areas which used to be all primarily rural are all going to be urban. Brown is urban. So by 2030, almost the entire world is going to be urban living, which means tall buildings. Right? So this course that we are now studying is going to be a foundation for providing or designing those tall buildings. These are some of the cities that you can see now. When we say tall, we will talk about what is really tall, what is meant by tall. Its definition is not universal. We'll talk about that. But you can see that congestion is going to force us to make buildings which are going to be tall. Another, this is a simple comparison. On the same plot of 50 meter by 50 meter approximately, if you have 2-story houses, you can accommodate about 10 small houses there. So 10 families can live there. In the same plot, if you make a 40-story building, about 200 families can live there. So you can see that on the same land with a 40-story building, you increase the occupancy by about 20 times. And that is the reason tall buildings are going to be extremely important. And then another new paradigm or new change in the urban planning is coming up. When the United States was developed in the 60s, if you look at the cities in US, almost all cities, they are planned in a very vast area like Los Angeles and other places. So single-story houses, wide streets, and everybody needs a car. Whole culture of US was based on car. So so if you look at that, they have the blocks and the cities, all of them designed like that. England is opposite. London is totally opposite to that. It's designed around metro, underground. So basically, they don't want cars. Hong Kong is like that. No cars. All the transport will be by public transport, by underground or trains. So what the difference between the two is environmental difference. Because people who live now in this compact city, they use much less gas, they use much less energy, they build much less roads, so they spoil much less environment. So from all those environmental considerations also, making tall buildings or making the living based on the public transport system is going to be the key. So that means city centers built around the public transport system, underground station around that building. Hong Kong is already completely like that now. Almost entire Hong Kong has become around. People don't own cars anymore at all. Hardly anybody owns a car. In Hong Kong, those of you who have gone there many times, this is the office building, and from here to the apartment building, there's an escalator, walk-a-lator. So people just stand and walk there because it's all compact city. So there's a whole cultural change which is coming, and cars are going to be out of fashion, which means that people will need tall buildings, multi-use buildings, office, accommodation, shopping mall, movie theaters, everything in one place, right? So for that, all that reason, tall buildings is going to be very important. What is tall? That is a very tricky question. If you go to New York, for example, or even now in Bangkok or in Hong Kong, and if you ask somebody, what is a tall building? They will say, yeah, 70-story, 80-story, 90-story. So they'll talk like that. You go to another city, let's say in Pakistan, in Lahore, what's a tall building? 25-story, right? Another city, 10-story. I have been to cities where they say we are designing a tall building, and how high is that? 10 stories. So 10 story is tall for them because that is the tallest building in that town. So tall is a relative term, right? It will depend a lot on where you are, what are the other buildings around you, and many times we get a request from somebody, they say, we are making the tallest building in the city. Like Myanmar, 30-story building is the tallest at that time. So the designer has to be really top-class designer to be given the task of designing a 30-story building. In Bangkok, we don't even care about 30-story buildings. Everybody is doing it. Even junior engineers are given 30-story building because seniors are doing 60 and 80 and 90 building. So it's also relative in terms of, so it could be based on total height, based on relative height, based on number of floors, services, and so on. But for us, structural engineers, our definition is very simple. If the building design is governed by lateral loads, it's a tall building for us. So if the lateral loads become important, earthquake and wind, more important than gravity load, then that means it's a tall building, because then the considerations for the tall building start to come in because of the lateral load system and all the things that we will talk about. So in fact, for us, any building in which lateral load become important or significant, or they override gravity load design, then it is a tall building. So some of the tall buildings that I will try to get a new projector, it's not so clear. Empire State Building was one of the first one, as you can see, around that nothing. And that was the start of the tall building whole, it's a symbol of tall buildings, Empire State Building. And after that, everything, this is like 1939, 1930, they made this building very quickly at that time. And then from that, most of the tall buildings followed. Then, of course, you remember, these buildings which were there, and then Petronas Towers and other buildings. Eiffel Tower, obviously, was the first tall structure to be made, but it was not a building, so it's a structure. Tall buildings, if you look at them, at top 10 tall buildings around the world, you will find an interesting thing. Where are they located? UAE, Saudi Arabia, Taiwan, China, Hong Kong, Malaysia, China, USA, China. All of them in Asia except one, right? So that means this is the region where now this century, all of the tall buildings are going to be mostly made. Hardly any in Europe, almost none, maybe few in USA, but almost all others will be here. So you are in the region where most of the tall buildings are. Everybody from US and UK who used to do their tall buildings are now have offices in this region. And you can see also the height of the buildings, the tall buildings, how they look like in the current way. Of course, there's another one taller than this one, which is almost 1 kilometer high. This is 800 meters. The tallest one is 1,000 meters in Saudi Arabia. They're making it now. And then China will try to cross that one, and so on and so forth. So for a long time, this remained the tallest building, but then others came, and then suddenly it started to go. This is how they look like in real scale. That is Eiffel Tower on the right-hand side, the last one, right? And this is how the Saudi Arabia the tower will look like. This is the one in Dubai, and then all of the other buildings. So you can see there's a going like this. Suddenly we have now a curve which is just, before it was more or less a little bit. You make a building, another one will make 2 meters above that, yeah. Some building form historical background. You can see some buildings where form was straightforward, then start to change like this, then so like this, like this. So CS Towers for a long time was the tallest building. No, I was telling you, before it was like this. You make a tall building, next one will be 2 meters higher than that, just to get the record. Now it's not 2 meters anymore. Now one is 800, the next one is 1,000 meters. Straight 200 meters. No, they don't want to make 810 meters because they want to make sure that the next one will not be easy to make. But, so that competition has changed the whole tall building design. So you can see from here, this is how the height is going down, right? So Number of tall buildings is also increasing in the last few years. This is the growth in height. So you can see up to 1000 meter, 1800 meter is possible. There was a time when most engineers, when we were studying, at that time everybody thought 100 stories was the limit, 300 meters. Then somebody came up with 500. Now it's 1000, 1200. The designs up to 400 meters are existing. They're just looking for somebody to finance it. 4-kilometer high buildings, right? The designs have already been, somebody has already created the design, the concept design, right? So you can see that this graph will go up very rapidly. So you can trace the whole history in architecture. 40s buildings were like that, very straightforward, rectangular form because they were made in very simple materials. Then the forms started to change, steps, then more forms, then many, fourth phase now it has architectural designs have evolved, and people are looking at form as an expression. But before it was just, make a building, so it's functional, you have enough space. One of the problems that was holding back the tall building is not structures, it was elevators. Because there were no elevators. So you could not make a building taller than 6-7 story building because who will go there? Then the elevators start to come. So the elevators technology has lagged behind structural engineering actually. So until recently, the maximum one, you remember last course I talked to you about a cable with the maximum length that it can take from a self-weight, right? That was a problem with the elevator. Because the cable that will pull the elevator, its self-load will become so long, no matter what you do, that will break by its self-weight. It cannot carry the elevator. So there was a limit on how long the elevator cable can be. That was about 300 meters, 320 meters. And that's where the elevator, so what the buildings did was, you have to change elevators. You go to 100 stories, then you change the elevator, and then next elevator will start again. So that was what people did in tall buildings. And then they came up with recently carbon fiber cables, very recently. And that limit is no longer there. Now, single elevator can travel up to 1 kilometer with the new material. And that has opened up all of these buildings. And the speed of the elevator has become very fast. It can go in 2.5 minutes to 1,000 meters, right? So elevators has been one of the reasons why tall buildings were not made too high. And now that technology has caught up, so structural engineering, and they are competing with each other where the technology will go. Now, problem is energy. Challenge of the current age is energy consumption in the building. It's no longer structures, it's no longer elevators. It is now the energy, because when we talk about environmental, I told you about that we are competing with transport. So, while if you make the building so big, so tall, and it consumes a lot of energy, then the energy you save for the people to travel in the city, if this energy is more than that, then it's not worth it. That means to make a tall building viable, challenge is to make it energy efficient. So now most of the new development is on making buildings energy efficient. How to make the building sustainable, environmentally economical in energy efficiency. So a lot of new awards for the buildings go to energy efficient buildings. Not on structural system anymore, but rather on which building has better energy efficiency. So water conservation, water recycling, energy cycling, all of those things are becoming very important part of the design. So first it was simple building, stone, whatever, then architectural considerations, then elevator, then structural problem, we didn't have enough structural systems, then it go back and forth, and now it's the energy. So anybody who solves the energy problem in a building, that can make a bigger building. China, there is a guy, I will show you later his design, you might have seen it. He's making a building now which he says is zero energy, because they are generating the energy within the building from different sources. Even doors, when you open and close, it generates energy. Right? People walk, they try to get energy from there. Right? So they try, and their building design is very interesting. The building is outside, and inside the building there is a spiral walkway going from the top to the bottom. It's a 120-story, 130-story building, but you can just walk on a ramp inside the building. So this is a multi-use buildings. People live here, they work here, the schools are also there, the hospitals are also there, shopping malls are also there. So people just walk up and down to reduce the elevator cost also. So things like that are now coming up in the tall building design. This is the breakthrough point for structural engineering. We will talk about structural forms a lot, but I'm just telling you that the breakthrough point in structural engineering, just like the elevator had a problem with the cable, steel cable, from steel cable they shift to carbon fiber, is a breakthrough point. For us, for structural engineers, tubular system is a breakthrough point. That the concept of a tubular system actually freed the structural engineers from the conventional problems of the structural system. And this was introduced by Dr. Fazlur Rahman, and he was one of the partners in a company in US, in Chicago. And after that, since his idea, every tall building and super tall building uses that concept. And that's why you see those buildings to be so similar. They are formed of tubes, 15 multi-cell tubes, 20 tubes, 21 tubes, 15 tubes. I will tell you what a tube is, how does it work. But tubular system is what made tall buildings possible. And this is currently, this is the way for the very tall buildings to go. These are two tubes, actually they were tubes. And one of the reasons they collapsed because of that plane hitting was the tubular concept did not account for such issues. But basically these were the first big applications of the tubular system. And then Chicago, in the Sears Towers and others. So these buildings were only possible because of the development of the tubular system. And we'll come back to this one. But basically tube means that you treat the whole building as one big cantilever rather than columns and beams and shear walls. So the entire building becomes one member with holes for openings, right? And then you treat that as and then you can put tubes inside tubes or multiple tubes side by side, and that's why you see the Dubai building having 15 tubes, same thing, 21 tubes in the other building. So different height tubes go up and down and they form the building. So tubular concept is the one that we use for super tall buildings. And he's the guy who developed that. He also developed many other structural systems. So he's one of the key person in tall building design. His development, his designs, his sort of concepts have actually helped for us, all the other engineers, to design tall buildings. And tubular system looks something like that. We will come back to this. So you can make a tube of any shape, any form, and then you can create a structural system based on that tubular concept. And these are some of his projects from Jafar Khan and his concept in the tubular system with bracing. So if the tubular system was not enough, he introduced this bracing, very interesting concept, brace tube system. And then he made this one also, and then these were also. So these are all possible buildings that are originally made in tubular concept. So we are basically dealing now with two types of tall buildings that we need to handle. One are the normal tall buildings, less than 300 meters, right? 200 meters, 300 meters, which are now becoming quite common. And then we are dealing with super tall buildings, 300 to 500. Now even a second term has come up, is the ultra super tall buildings, which is above 500 meters. because they are a different category altogether. Now we already have 6-7 buildings in the world which cross that line, and the one in Bangkok is also going to be 600 meters. So these are really, really tall buildings. Currently, the tallest building in Bangkok is 300 meters. So the next one is going to be 600 meters, not 320 meters. Double from that height, suddenly. So these are, and then architectural expressions, forms, many things are going on into, and China and Dubai are the leaders currently in the world for tall buildings, innovations, construction-wise, design-wise, form-wise, energy-wise, everything. They are, all of the major development is going on into those two countries. Okay, now if you look at the tall building, actually it's one of the projects where many people, many different type of people have to work together. Unlike a bridge, unlike a dam, unlike a road, unlike other structures, other systems where one or two professionals are normally working. Of course, those things are also becoming complex now because of the automations, but tall buildings particularly relies on many working of many people together. And one of the key component of a tall building is the service core. You will see that service core is the key in a tall building for everybody. That is the place which everybody uses to put their own design there. And around that then is the area used by the public. So service core means that it contains the elevators, it contains the stairwells, it contains the heating and ventilation ducts, it contains plumbing and piping and all of that stuff, electrical, communications and security and everything. It is contained in that service core. And that is also where we engineers, structural engineers, put our structural components most of the time, right? Shear walls. So shear walls are generally put in the service core, or let's say service core is put inside the shear walls. Either way, how you call it. So service core is the key. So a tall building is designed around one or more service cores, right? And they service everybody. And often you will see some plans, the service core area is larger than the area available for actual usage as the building becomes taller. Because you have to put too many elevators. You cannot put few elevators. When the building becomes taller, then you have to put maybe 20 elevators. So 20 elevators take a huge space, and you cannot make a tall building too big because of the wind and earthquake and other things. So the service core is the key, and around that you find some small areas left for people to use with a view. So people pay a very high price for a small area in a tall building because of the, now you can see from here, that's how, so that's the service core. That is the service core. That is the service core, service core, service core. And inside here, service core. This is not a service core building. This is a much smaller building. So you can see the service core takes up often central place, often, not always. This is the side, and then around that you have the usable space. And this is the most common plan of a tall building, looks like this, right? And this is where you put your structural elements. And tubular system, the tube is put outside, and the core walls are put inside. Okay, so they work together. Today we are just looking at things. We are not studying anything. Just giving you some idea. This is one of the buildings in Bangkok. Those of you who have seen Central World, right? Central World has a tall tower on the side. The hotel is, that is based on this concept. This is the plan for that core. So you can see the service core is huge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 elevators. each cross is the elevator, right? So elevators are taking almost all the space, and then some staircase, and then so this area is all service core, and this is the only area left around that for people to use. Another big building, see all systems place. This is a very nice, beautiful building in Bangkok. Conrad Hotel and all that. If you go to that side, you can see. Look at the service core, and that is the only area left outside for people to use. So service core takes up a major portion of the building. This is only 65-story high, not even very tall, right? The service core is quite big, and you can see elevators. So many things need to be there. So it's a very highly complex area where everybody is fighting for space. Electrical engineers, mechanical engineers, security engineers, communication engineers, structural engineers, architects, fire engineers, everybody is fighting over this space, right? Because everybody needs to have their system designed within that. So this is one of the key problems in tall buildings. All these professionals trying to control this space. Another building, Fullerton Hotel building, but this one is core is here, but there are other elements here. So some other buildings in Philippines that we have designed, residential apartment. These are actually all 6-7 buildings of a single plot. Now they are mostly complete, and this is the tallest building currently in Manila. It's about 72, 73 stories, not that tall, but in Manila, tall buildings are not possible because of the heavy earthquake, high earthquake loads. So this is the tallest building currently over there. So, in architecture, they teach them about two things, form and function, right? Everything that they design has a function and has a form. And the fight between form and function is a fight between architects and engineers, a lot of time, and architects and other people, and architects and cost. Because many of the, not all, many of the architects want to concentrate on the form, and they sacrifice function. In fact, all of the 7 wonders are just form, hardly any function. They do nothing. They just are there to convey some message or make something look great, but do nothing. Right? Monuments are just form, no function. Right? Warehouse is all function, no form. Right? So there is a in between. Currently, this pluralism that we call it, two things to be balanced together, is now third item is a monument, which is not here. So in fact, the third one is now a monument. So the balance between form, function, and environment is now the challenge for the tall buildings. So this is the key behind that for us. Structural theory is kind of universal. That means no matter what the problem is, where we are making it, who is making it doesn't matter for us. It's a structure, it's a column, it's a beam, it's a wall, it's a rebar, it's a bending moment, it's a shear force, right? It is universal. It absolutely doesn't matter where, when, who is making it, for what purpose. For us, it is bending moment and shear force, stress and strain. Ultimately, last time I told you it's all about axial strength and axial stress, correct? So that's it. We only know that. So for us, it is universal. For architect, it's not. For them, every building has to be unique because the culture may be different, the city may be different, the environment may be different, the sky may be different, the sun may be rising from a different direction, the people's color may be different, and so on and so forth. So for them, a challenge is that every building has to be according to time and place. For us, it's timeless. So a building is actually made up of many systems. Basic functional system and architecture, which the architects will normally plan. Then structural system, where you will come in heat, ventilation, air conditioning system, very important for a building. Plumbing and drainage system, again very important for them. Fire safety, cladding systems, security systems, and other specialized systems. So many people have to work. I forgot landscaping and interior decorators here. They are also becoming very important now. Okay. And other people are coming in now. Actually, this list is not complete. So the team is organized like this one: in design phase, in construction phase, in coordination phase, and then so you have the project. There are various phases in the project. So huge teams, contractors, and so many people. So this is something that you cannot see clearly on the screen, but when you get the notes, please look at that. And the work breakdown, how the work is broken down. We will come back to these later. But just I'm trying to tell you, there are many people involved. These are the things to be done. This is the type of work, and then who is doing what. For example, if it's a tall building and structure has to be designed, then who will design it, who will check it, who will verify it, who will advise on it. So all types of actions during a process by different people for different tasks are listed in one sheet. So everybody knows exactly who is doing what, right? So the responsibility is divided into many categories: approval, assisting, helping, so things like that. And then you put those dots, and this shows, okay, this is a complete picture of what people are going to do for this particular thing, right? When you make any proposal for a project, a client will ask you, give me your responsibility matrix, so I can see if something goes wrong, whose neck I will catch, basically, right? Also shows you hierarchy of doing things. So these all things you can see. One more important thing in the responsibility matrix or the responsibility category is, what if something goes wrong in a building? Whose responsibility is it? It's a tricky question, because in a building we have the client and the owner, we have the architects, we have the structural engineers, geotechnical engineers, people who check the design, and builders and contractors who make the buildings. And on the other hand, we have the building codes, structural design codes, lawmakers, building officials, legal and judicial system. And then there is a public user and occupant. Now the question is, if something goes wrong in this building, let's say it falls down, and some people are hurt or killed, whose responsibility is amongst all these people? So this is a very complex issue. Insurance companies don't know what to do in this case, right? Because this building may be insured. So finally you may make the claim to the insurance company, right? Who has insured the building. But insurance company would like to get to see who's the one who's at fault, and that's where the investigation comes in. But at that time, we have got to not just follow the code, because everything may have been followed exactly, but still something went wrong. Then it becomes a challenge. Design is okay, construction was okay, everything is okay, but still something went wrong, right? So then it becomes a challenge, and then we need to do more sophisticated analysis than the building codes will allow, and we will talk about that in the second part of the midterm in performance-based design. Okay? So, just to conclude, architects normally are the team leaders for the tall buildings, so we have to accept that this is an architect's project. Unlike a bridge, where a structural engineer may be in charge, building is an architect. So if you want to excel as a structural engineer, to show off your work, bridge is where you might go. But even that now is being taken over by architects, because people want nice bridges. One of the things that we don't do well is aesthetics. Engineers are very bad at making nice things. They always make the ugly things, and people don't like that. So that's why engineers are not really respected, because we don't know about the statics, right? We just want to do simple, straightforward things in very poor way. So that's why architects tend to take all of the main work and most of the money also. Then geotechnical engineers who look at the soil, right? Electrical electronics engineers who look at all of these things. Mechanical engineers, mechanical system. Plumbing engineers, construction engineers, communications, landscape, fire safety, security consulting. Tools of the trade for us. These are the software that you will be using in this course, or most of them anyway, or some of them anyway. Okay, so better get used to it. Okay, ETABS, primarily our main program to use in this course will be ETABS. Okay, so some of the items that, some of the new systems people have been developing recently that we just talked about, some basic systems we will talk about, and some innovative system. Innovative means that depending on the project needs, they have come up with some combination of many systems together, and some of these buildings are examples of that, and we will talk about that later. Especially these ones here. These ones here, you can see that the problem is that multiple towers are connected by bridges, and this creates a huge problem in dynamic response because each building is trying to move independently, and then the bridges connect them. So the question will always be whether this bridge connection should be rigid or flexible, and how flexible. And so this creates some of a challenge in all the times when we have these buildings which are connected by bridge. The biggest example is the two buildings in Malaysia, as you know, the big towers connected by a bridge. So that was one of the first main buildings where they did that, and that actually is a flexible connection. So when the tower moves, the bridge slides between them. So it's a very complicated arrangement is needed to do that. This you can see here, the building is changing the form completely. So conventional systems may not work in that location. And then we also have this new concept of the diagrid, which is now becoming quite popular. That means instead of making vertical columns, all the columns and all of the members are inclined. So no beams, no columns. So these are inclined members which form like a shell outside. So this diagrid becomes the primary system both for lateral and vertical load transfer at the same time. So inclined member, not a column, not a beam. So diagrids are becoming quite popular, and some big examples are these buildings. And this is also a very challenging building with diagrid and inclined wall here, and created some really interesting problem during construction, because during construction things are not exactly aligned, and also there's a creep, there is a movement. So how do you accommodate all of that while the construction is going on? So a lot of careful planning and design is needed for buildings of this kind. So another important development in the recent years is BRB systems, buckling restraint braces, and we are now using them in many buildings, and this has recently become a very important type of structural system, which is a combination of a temper and a brace. So it's a kind of a brace which never buckles, and so we have talked about buckling in columns. So no matter how much load we apply, this will never buckle. So it will yield before buckling, and that is a very important property that we need for dynamic and lateral response. So we use this brace as a brace and temper at the same time. So now quite a popular structural component. AIT has done a lot of research on testing and developing. In fact, even manufacturing BRB and providing on the projects, our students and our people have done that. So this is quite an interesting development that we will also discuss. Fabrication wise, you can see that sometimes buildings, complete units are made, fabricated and simply connected together. As you can see, full walls, even full rooms, complete, made and installed. You can see large panels of walls and buildings. This is all just long walls and panels fabricated and simply connected together. And this creates a problem in lateral response because these joints have to be designed to provide fixity. Recently, we looked at a 30-story building in Thailand, which is made from precast panels, wall panels entirely, and precast slabs. So it's a very challenging project, especially when we talk about earthquake response of these buildings, which are precast and not cast in place, right? So these are some of the innovative and challenging things that tall buildings also present. Slip forming is another way of doing construction, which affects the design as well. That means continuous forming. So you make something and it continuously climbs. It's not something that you make today and next week. In 24 hours, it keeps on constructing and climbing by itself. So this is like a slip form. So they are casting concrete continuously, and the slip form climbs onto the wall which is already casted previous day. So very, very slowly and continuously, it keeps on climbing and forming the wall at the same time. So the slip forming is a interesting way of doing things. And then normally the core walls are made first by slip forming, and the slabs are then connected. They follow behind. So that creates a construction scenario which you do not consider in design. So that needs to be analyzed also. These days it is becoming quite important to not only analyze the buildings for the final condition, but also the condition of the building during construction. Because during construction, the building is much different from what it is going to be. So that means you not only have to analyze and design the building as completed, but also as the construction progresses. And that is called construction sequence analysis, which we will also talk about after the midterm. So these kind of things are all important. And another interesting development is the top-down construction. Normally we imagine buildings that we go from bottom upwards, but there's also a way to go from top to down and from here to up at the same time. Because as you might have seen, that a lot of buildings spend a lot of time in foundations and basements, and it takes years before they finish that. So then they finish and then they have to construct, and this is not good. People want to do it quickly. So they start at the ground level, go down and go up at the same time. So this is quite interesting that you can start immediately going up and down at the same time. So this is called top-down construction. And Professor Naveed here is quite an expert in that kind of work. And there are a couple of buildings in Thailand which have been made like that. State Tower is one of them. So the idea is that first you just build these piles, and then from that, on that piles you start the construction upward and start digging downward at the same time. So when Dr. Naveed will take one class on foundation, he will talk about this with you. So obviously again, the problem is construction sequence. So it is not just that you model the building and analyze, you also have to see how it is going to be constructed, because it's going to affect how you analyze and design it. Modular construction, this is a building. You should go to YouTube and check this building, 30-story building built in 15 days. Type that on the internet, you might have seen it already. If not, you should go and see the YouTube video for this particular project. Very interesting. They make a 30-story building in just 15 days, complete. That's it. So normally 30-story building should take minimum 30 weeks if you go very fast. Typical construction is 1 story per week. If you can do 1 story per week, it's already quite fast, right? So it should take 30 weeks, which is 210 days, and they finish in 15 days. So obviously a completely different way of doing things and very fast. And the same company is now trying to build a 120-story building using the same concept. Okay? So you should check this whole thing out. Then concrete printing. Now, as you know, 3D printing is coming up. How many people know what is 3D printing? You all know, right? Yes? No? 3D printing is now that you have printers which instead of printing on paper, dot matrix printer used to print like this. If you remember, maybe you don't even have seen a dot matrix printer. So they used to print dot by dot on a paper, and it was a popular way of printing a few years ago. Now the same thing is being done 3D. Instead of printing ink, they print some material. So they move this way and that way and keep printing or keep depositing material, but also keep on going up and down. So they can create a whole 3D object just by printing. And this is some example, real example. You can see it is printing the wall with a diagonal bracing. So two cavity wall is being printed with the bracing. So it's a cavity wall, it has a good insulation, it has everything that you need, and you can print it in any form. No need to start joining anything. The joints and connections, everything will be just right. So you can see here, that's the printing, and that's the big one, full printer. So basically the 3D printer is a crane, and it is a pump on that, and it moves both ways and prints where it wants. They're not so complicated in concept, just like a dot matrix printer, right? So that's all, the whole house is being printed here from that 3D printer. You can see from there. So these are all the things that we may be seeing very soon. Foundation and big basements, we will talk about that. There is also development in that in terms of how to make very deep basements, because parking spaces, people need 7-6 stories below ground. So how to make them quickly and in a reliable manner. Important thing, sustainability in tall buildings, I talked about a little bit. This is another very important aspect that everybody will be talking about. Sustainability of tall buildings, and everybody has to sort of think about it. You cannot just only think about strength, and you cannot think about shear and moment. You have to think about sustainability at the same time. Whatever you are doing, engineer, architect, everyone, planner, everyone have to think about sustainability as one of the aspects. So that's going to be part of something that you should consider. Measuring sustainability, there are many ways to measure how building is sustainable. It should use minimum material. There are whole guidelines, the reuse of existing materials, and minimum energy, and whatever. So there are many ratings, and there are rating systems, so you can evaluate your building and get a rating of platinum or gold or silver. And then it costs a lot right now to make a sustainable building, but many people do it because it creates like a vision for the industry. For example, in Thailand, SEG is a big company, and they have just made their head office as a very green, platinum rated building. Cost them a lot, but now everybody says SEG made a green, platinum rated building. So that's an image that people associate with. Right now it's an image thing, but ultimately this is something that everybody will have to do. So sustainability is something that you will need to talk about: energy demand, energy resources, operational and embodied energy, waste reduction, reuse, recycling, transport to go there and go to build the material, community, health, well-being, everything will have to be integrated, because building is not just stone and concrete anymore. It has to be thought about a place where people work and live and use, right? So a very big sort of vision is needed for everybody to work now. So if you don't know about sustainability, and if there's a meeting going on about the building and you don't know what they're talking about, then maybe next time you will not be invited. So we need to be aware of the other aspects. Sustainable construction of tall buildings, natural elements, you need to utilize natural elements so that heating, cooling, daylighting, and rainwater collection, solar power, wind power, all these things are part of the design. Of course, as a structural engineer, you may not be directly involved with them, but it will affect your structure that you're designing, and also the material that you select. And so, for example, if you reduce the beam size, it's not just about the cost. It also means less concrete, less breaking of the mountain to get the aggregate, less breaking of the mountain to make the cement, less cement to be transported, less gravel to be transported. So it's not just the cost per kg or whatever, it's the environmental impact of that cost that also is important. So when you measure, when you look at the design, you need to look at the entire life cycle. People are also talking about how much will it cost to dismantle that building. So your building should be designed to be dismantled. Now they have to explode them, right? And they come down and they cause a lot of smoke and dust. So people are worried about that because every building has a lifetime. It has to be demolished. So that has to be part of the design, how it will be demolished. So minimum land, tall buildings. So by definition, tall buildings can be sustainable because they use least land. So least land will be affected by the construction compared to other buildings. Building form and use, designed for flexible use. That means the building should be able to use multi-use, flexible use. So it is not, so if you design it to be, let's say today you design it to be an apartment building and there is no demand for apartment anymore, the building will be standing there. But if it is flexible use, it can be converted into an office or university or a college or something like that. So flexible design is like that. Floor plate impact, tall building structure, structural stability, efficiency, all of these are things that we need to consider. Energy embedded in the material is something that we have to consider. How much energy did it take to make that material? Embodied energy. So when we select a material, we have to look at how much energy did it go into making the material right from the beginning to the end until it came to the building. Not just, so you have to talk about, excavation, to the power to generate, to burn it, to fuel, to bring it here, to lift it up, everything. So all those aspects are considered. Construction industry research and implementation. So now if you go to construction industry, you will find that a lot of talk is about sustainability. Services. I've already talked about a little bit of that. So building services and design issues, energy, we talked about heating loads, electrical lighting, all of that, fire safety, vertical transportation, water and wastewater, all of that. You may not think right now that this is related to you, but that is the problem that the professions are trying to solve, that everybody should think about everything. Otherwise, everybody is just in their own well and problems do not get solved. Most of the sustainability issues are related to construction process. During construction, a lot of environmental impact is created through waste, through noise, through pollution. So the construction process has to be sustainable too. No wastage of water, no wastage of material. How do you dispose of the waste material? How do you recycle what is out there? And how do you conserve energy during the process? Alright, so that's just about overview of the tall building